So some functions are defined based on different rules for different input values. And these are called piecewise functions. And that's actually what this small subsection here is about. So let's fill that in. And the examples that we look at are going to be, in particular, we can say that they're going to be defined based on different rules for different ranges of input values or different intervals of input values. Okay, and a classical example of this is actually the absolute value function. So that's the one we're going to look at in this example. So the absolute value function is defined in the following manner. So if I want to write down a rule that tells me how to compute the absolute value, say, of some real number x, well, I can use this method to do it, which is essentially a perfect example of a piecewise function. So I define it in two different ways depending on the sign of x. Okay, so if x itself, the number x, in between these two vertical lines, that's the notation for an absolute value, by the way. This is an absolute value calculation if I just have two vertical lines surrounding the letter x or the number x. So if x happens to be positive or 0, so in other words if it's non-negative, then the result is just whatever x was. So it's going to be x if x is greater than or equal to 0. But if x is a negative number, well, then what effect does the absolute value have on a negative number? It just throws the negative away, right? So that I'm going to actually return, in this case, negative x if x is less than 0. Now, I just want to pause here for a moment because a lot of times when I cover this at this point in the course, I get a couple of sideways looks because people don't quite understand where this negative comes from. Think of it this way. If x itself is actually a negative number, well then what would happen if you put a negative sign in front of x? Well, if you put a negative in front of a negative number, you actually flip the sign and make it a positive number. And that's exactly what the absolute value ought to do to a negative number. So that's in fact exactly what you want. Okay, so this is an example of a piecewise function. Let me do a few calculations where I show you how you would use this rule if somebody presented it to you. Okay, so let's calculate a few absolute values. Let's say I wanted to take the absolute value of the real number 4. Okay, so, well, how would I do this? I take the number 4 and I plug it in for x, and I notice, okay, this is a piecewise function. So what do? First thing I do is I actually jump over these rules here, and I jump over to these conditions, and I say, okay, which of these conditions is satisfied when x is equal to 4? And, well, it's not the bottom one, because if I put x equals 4 here, I'd have 4 is less than 0, and that's not a true statement. Right? But if I put x equals 4 into the top condition, I'd have 4 is greater than or equal to 0, and that's certainly true. So if this condition is true, that means I want to use this rule to calculate the output value for this piecewise function. So what I'm going to do now is I'm going to take this value 4, when I plug it in here, I jump and I use this rule and I plug it in here because this condition was true. Okay, so, well, if x is equal to 4, well, I'm just going to return 4. So this is just going to return the number 4. And that's since 4 is greater than or equal to 0. Now, if that seemed a bit weird, don't worry, we're going to do a few more examples, so you'll get the hang of it by the time we're done. So if I were to say now, let's try a different number, 0. Let's plug in the number 0. Well, take the number 0, plug it in for x, jump over these rules and look at these conditions and ask yourself which of these two conditions is true when x is equal to 0. And the answer is the top one, right? Because 0 is greater than or equal to 0. So that means we're going to use this rule again. So if x is equal to 0, then we're just going to return 0. So that's what that'll do. So we'll get that, and that is because 0 is greater than or equal to 0. So both times it was the top condition that was true. So both times we used this rule to compute the output value. So in both cases, the output was just exactly what x was. In this case, x was 4, so that the output was 4. In this case, the input was 0, so the output was 0, right? Because we were using this rule. Let's do a couple of different examples. How about a negative example? Let's take the absolute value of negative 3. So we're going to take negative 3 and plug it in for x. So jump past the rules for now and just look at the conditions. Which of these two conditions is true when x is equal to negative 3? And the answer is this one, because negative 3 is less than 0. Okay, good. So that means now we're going to use this rule to calculate the output of the absolute value function, where x is negative 3, right? We put in negative 3 for x, so we're going to put a negative 3 here. So, but this negative in the formula is still going to be there. So we actually have negative 3. And you see how that worked? See, now we have two negatives. And what happens with the double negative? They cancel out, and the result is a positive number. So you end up getting 3. So the absolute value actually did exactly what it's supposed to do. It threw away the negative, but the way it did it was by putting another negative sign in front to cancel with that negative. Okay, so well, the result was 3, and the reason we used this rule, that's because negative 3 is satisfied this inequality, right? Because negative 3 is less than 0. Okay, and then let's just do one more for good measure. The absolute value of negative 1. Take negative 1, plug it in for x, jump across the rules, go to the conditions. Which one's true? The bottom one, right? When x is equal to negative 1, the bottom condition is true. That means we're going to use this rule. So plug negative 1 into this expression. So you're going to get negative 1, which actually equals positive 1. And this is for the same reason, since negative 1 is less than 0. Really what the absolute value function does, and this is another way to think about it, is it takes as input some real number x, and then it measures the distance along the number line between x and 0. And then whatever the distance is, it returns that as the output. That's another way to think about it. But this definition using a piecewise function is absolutely fine. In fact, this is the actual formal definition of the absolute value. So that's an example of a piecewise function. And one thing worth noting, I've got room for a note down here, you're always going to get a positive number. The only time this negative appears is if x itself is already negative, right? So if x is positive, then it's just x is going to be returned. Or if x is 0, then just x is going to be returned. So you'll always get a non-negative number. So the way we can say that, we can say the absolute value of x is greater than or equal to 0 for every real number x. Okay, so that's just a property of the absolute value function. Okay, what else do we have on this page? We've got another example. So we want to find f of 0, f of 1, and f of 2, and sketch the graph of f, where what is f? F is the piecewise function that's defined down here. Okay, so it's f of x is determined by the rule 1 minus x for values of x that are less than or equal to 1, and f of x is determined by the rule x squared if x happens to be greater than 1. That's how you can read these too. Okay, so let's start by computing these three quantities, and then we'll worry about sketching the graph afterwards. So let's compute f of 0. So how do you do this? You want to compute f of 0, take 0, plug it in for x, jump across, skip the rules again, go right to the conditions. Which of these conditions is satisfied when x is equal to 0? And it's the first one, right? It's the top one, because 0 is less than or equal to 1. So we're going to use this rule to calculate the output value. We're going to plug 0 in for x in the top rule. So we're going to get 1 minus 0, which is 1. So that's how you compute f of 0. F of 1, well, let's plug 1 in for x. Again, it's the top rule, or pardon me, the top condition that's satisfied when x is equal to 1. So we're going to use the top rule. So plug x equals 1 into this expression. You get 1 minus 1, which is 0. And then the last one, f of 2. So take x, plug it in for 2, and now it's going to be this condition that's satisfied for x is equal to 2, right? Because 2 is greater than 1. So we're going to plug 2 into this expression. We're not going to plug it into the top one. We're going to plug it into x squared. So plug in 2 here, and you get 2 squared, which is equal to 4. So that's how you can work out these first three quantities. This is just, the purpose of this is just to give you a chance to spend a few minutes practicing and refreshing yourself on how to evaluate piecewise functions at points. But now, how do you sketch the graphs of these things? Well, you have to be careful, but you can do it in the following manner. Let me just draw a pair of axes here. So draw the Cartesian plane. Just give that a moment. You got the x-axis, the y-axis, and now, okay, the origin's right here, and now we have to draw the graph. So whenever you're dealing with piecewise functions, the first thing you should look at is over here. At what point, at what x value, does the behavior change? And it looks like the number is 1, right? To the left of 1, the behavior of the function is given by the rule 1 minus x. But to the right of 1 on the number line, or on the x-axis, the rule that defines the function is this x squared rule. So the number 1 is exactly where the behavior changes, right? So that's why I want to make sure I actually plot that on the graph, and I'm going to label it very clearly. And actually, I'm even going to sketch a vertical line here to help keep things organized, because this is not part of your graph, and that's why I use hyphenated line, just like when we were doing doing an illustration with the vertical line test on the previous page. So that's not part of the graph, but it just helps to keep things organized. So let's start over here to the left of that line, and let's sketch the graph of the function f over on this range. So the values of x that are less than or equal to 1. Well, on those values, the function is defined by this rule. Let me just write some rough work over here. If I had the equation y equals 1 minus x, right, if I just set y equal to this rule up here, which is the rule that I'm going to be using on this piece of the graph because that's the condition x is less than or equal to 1, what is this? This is actually, if I write it a little bit differently, it looks familiar. If I write it as y equals negative x plus 1, what you really have is a 45-degree line facing downward, but shifted up 1 unit, right? This is a line with slope negative 1 with y-intercept positive 1. So why don't we start by drawing 1 on the y-axis, and we know that we're going to actually hit the y-axis at that point. And since the slope is negative 1, we'll talk more about slope in the next section as a more thorough refresher, but for now, if you have a slope of negative 1, that means the line goes down 1 over 1, down 1 over 1, down 1 over 1, right? You're going to go downward at a 45-degree angle. But hang on, we don't want to go too far because we're only going to be following that shape to the left of this green line, right? Because that's only going to, this rule is only applied, you can see it underneath the ruler, for values of x that are less than or equal to 1. So we're going to have something like this. Okay, so that's part of our graph. And I'm going to do a solid dot here because I want to include that point because this allows for the case where x is equal to 1. And if you plug in 1 for f, you get 0. So this actually is a point on the graph, right? F of 1 equals 0. That means the point 1, 0 is on the graph. So that takes care of the left half. Now what about the x squared? Remember what x squared is? That's just an upward facing parabola centered at the origin. And this is where you'll see that I switched to my pencil here. I just want to really draw a really faint sketch of the parabola y equals x squared. But it's not perfect, right? But that's, you can see it just very faintly. That's the idea behind the parabola, the y equals x squared. But I'm going to erase part of this because not all of that's going to be relevant, right? For this function f, it's only going to behave like that parabola for values of x that are greater than 1 and strictly greater than 1. So really, it's just this piece over here that we want. All of this stuff to the left of the green line is going to get erased. But it's helpful to draw it just to remind yourself the shape of that parabola. But we really only want to keep this portion of the graph. And that should be nice and curved, but I drew it a bit straight. But this is going to be a nice curve going up. Okay, and all this other stuff, let's erase that because that shouldn't be there. That's why I did it in pencil, because it's going to be non-permanent. Okay, so that's a pretty decent sketch, right? And then if you keep going to the right, this curve is going to go up steeper and steeper. But that's the graph. So that's how you can graph piecewise functions. Again, start with the breakpoint, or I guess boundary points, whatever you want to call them. The place, the x values where the function changes from one behavior to the other, and start by labeling those points and draw little vertical lines. And then you're just going to focus on each segment of the graph one at a time.